Hello everyone. Today we will solve LeetCode question 314 binary tree vertical order traversal. So this question description is like, given the root of a binary tree, return the vertical order traversal of its nodes values from top to bottom, column by column. So it basically wants us to consider this tree column by column, and also starting from top to bottom, iterate level by level, and create groups of nodes as shown in this example output. And the order will be like, start from the leftmost column, go towards rightmost column, and in the case that where one column has multiple nodes like this one, the order will be from top to bottom. Alright, so now that we have understood the question, we can think about how to approach this problem. And the first thing I notice is it expects us to make this traversal from top to bottom, right? So this makes me think about breadth-first search, because if I do BFS, then I will be visiting this tree level by level, starting from 3 and then visiting 9 and 20. So if I can make a BFS solution, then it means that I will have already handled top to bottom condition. Alright, so what about the other condition? Visiting column by column, creating groups of columns. So one thing is certain, we have to keep track of which column are we visiting for each of these nodes. So if you consider the column ID of the root node as 0 here, then we can create a numbering, like if we are moving towards a left child, we can make it less by 1. If we are moving towards right, we can make that column more by 1. And by this way, we can create these column numbers, right? -1, 0, 1, 2. And if we do this, then we can just create a Python dictionary in which the key is the column ID, and then it basically keeps a list of node values. Right. So if we do this, then we can just, at the final level, we can just start from minimum column ID to maximum column ID, and then create a result. So this should work. And then if we think about the time and space complexity of this, we are just doing a BFS and it then create the solution. So this means that we will visit each of these nodes just once. So this will mean that the time complexity will be ON, and the space complexity is, we will need a queue to make the BFS iteration, which is ON space complexity, and also we need to do this grouping dictionary, which will again introduce ON space complexity. So overall, we will have a ON time and ON space complexity solution. All right, so the solution now makes sense, and we can move to the coding part. All right, now let's start coding. So first we need to handle the case where root is none. We should check it like this and return an empty list if there's no root. And then I will keep the column dictionary that we talked about, and here I will use default dict list because we want the values to be lists, and I'm using default dict to not bother with inserting keys and initializations and key not found errors. Then I need this queue for doing the BFS iteration, and it needs to have a tuple, right? This is because I both need to keep track of the node and also its column ID. Initially, this will be 0 for root node, and here I am keeping node and column for remembering this. All right, and one detail is I actually want to convert this to a double-ended queue, a deck, and this is because I will need a pop left operation for implementing BFS traversal, and if we just use the list and do like pop 0, then it will be on time complexity. This is because of how lists are implemented in Python, but if you use DEC, then we can get constant time for pop left operation. So that's why I am using a DEC here. Right, and I'm starting the iteration. As long as we have elements in the queue, then we just need to pop q dot pop left, and this will give us the current node and column. Now that we know the column of these nodes, we can just populate it in the column dictionary, and we can say like col dot append node value. And here I'm appending not the node itself, but the node value, because in the response we should have a list integer, and those integers are just node values. And here we notice that we can, without first creating a call entry in the column dictionary with a like empty list, we can just append it. This is thanks to default dict. Now, as in the classical BFS implementation, we will just do like if node left exists, we will just append this left child with the same format like a tuple with node left, and column is going to be -1 because we are moving toward left. This is the numbering that we first designed, and now I'm doing the same thing for the right child with +1. Now I can just create the final result. This will be return, and to do this I basically need to iterate on all the columns, but here the problem is we need to iterate from the minimum column to the maximum column to fulfill the requirement that we should be moving from the leftmost column to the rightmost column. To do this, one way is to just sort the column dict, but we don't want to do that because we can do more efficient. As we know, sorting is n log n, but we can actually iterate on columns in the linear way, and we can just do this. And to do that, we just need the minimum column number and the maximum column ID, right? And it's just easy to create two variables here. We can say minimum column and maximum column and initialize them as 0. And then while we are iterating here, when we fetch a new column ID, we can just update these values. So minimum column and maximum column will be updated here, like minimum column and maximum of maximum column and the current column. So if we do this, then at this point we just know the minimum column to start from and iterate until maximum column, but we need a +1 here. This is how range function works. If I do this, the last number that this range generates is max column. This is just what we want. And then we can just append the result column dict call. So this will give us a list of nodes at this column, and we append to the result, and then we just can return result. So that's all with the implementation. Actually, we just need to create a dictionary and to store all the values by their column numbers, and it's helpful to keep track of minimum column and maximum column numbers during BFS iteration to avoid sorting it at the end. And as long as we have elements in the queue, we will just pop it, and this will give us the current node and column. We will just populate column dict using this column and node, and as in the classical usual BFS implementation, we will append the left child and right child to the queue if they exist, with col -1 and col +1, depending on the left and right child. So that's all with the solution. Okay, so in most interview settings, you're actually expected to do the verification. What this means is coming up with some test cases and trying out some edge cases and execute your code manually line by line and to see if it actually works and catch any bugs if there is and fix them. So I will try to do that as well with a small simple input. So let me put here an example input like this. Okay, so in this input we have a simple tree structure, but yeah, let's verify that this actually works for our implementation. So initially we will just put 1 and 0 here as root and column number, and when you pop them we will have 1 and 0 here, and this is popped from here, and the queue looks like this now. And the column dict here will now have this entry. So there is this 0, and 0 has this list which has 1. And then minimum and maximum values will be updated as well, but they will remain 0. If we look at here, we see that there are both left and right trees. Left is 2, right is 3. So we are here basically appending to queue, and it will look like we have 2 here, and the column will be -1 because it's going towards left, and 3 for that we will have column 1. In the next iteration we will just pop these values. So notice now 2 and the column is -1. This is popped from here, and we are creating a new entry in column dict, and this will look like for column -1 we have this list with node 2. All right, and now the minimum column will be updated as well. Minimum is now -1. If you look at the children, for this one there is only left child, which is 4. So we will here append a new child 4, and the column will be -2, -1, -1, that's -2. And then we will iterate again. We will pop 3, 1 this time. So notice 3, column is 1, this is popped. And we will update the column dict. It will look like this. For entry 1, for key 1, we have 3. All right, and we update maximum column. It will be 1. And looking at the children, we have only 5. That's the right child of 3. And for this one, we will append here 5 and 2. All right. Now we will iterate again, and we will start from 4 and here -2, and we need to create this entry here -2, having the list with a single element 4, and we need to update minimum column as -2, and we will check the children of 4 which do not exist. Then we will iterate again. So this is already popped. We only have 5 and 2. For this one, we will create a new entry. Key is 2, and the list has only 5. We will update max column as 2, and we are checking the children. There is none, so the queue iteration is complete. At this point, the column dict looks like this. And also minimum column and maximum column are -2 to +2, and this range operation will generate all these numbers up to 2, and for all of these we will just fetch the correct element, and result will look like, so we will first get the value for -2, and that's 4, and for -1 we will have 2. For 0 we have 1. For 1, 3, and finally for 2 we have 5. Okay, so this is the expected results for this, and if you look at here, we should actually expect 4, 2, 1 and 3, 5. Each of them should be a list, but all of these lists should have a single element, and our code exactly produces this. This is an example of how you can do code verification. Finally, I want to discuss time and space complexity of this solution. So if you look at time complexity, we have this BFS iteration, and the BFS will basically process each of these nodes once. If we represent the number of nodes in the tree as n, this will cause us on time complexity because of BFS. And then we are iterating here on all of these columns, and this column dict call indexing operation will be constant on average. So this will have a cost in the order of number of columns, but since number of columns are bounded by number of nodes, this will still yield us on time complexity. For space complexity, we are creating two variables that are not constant, which are column dict and q. The other ones are just O1 space variables. For column dict, we are basically putting all of the nodes in the tree into this dict and group them by their column numbers. So column dict will cause an ON space complexity. For the other variable, the q, the size of this q is proportional to the largest level. That is, if we consider a case where we have a complete tree, complete binary tree that looks like this, if you consider all the number of nodes in these tree are n, then at the last level we will have n divided by 2 nodes. So this means that the q in this case will be bounded by n divided by 2, and this again causes ON space complexity. So the overall space complexity will be again ON. At the end, we have an ON time and space solution. So that's all for this question. So I appreciate if you leave comments, questions, like or subscribe. So yeah, thank you very much.